Eniola, I can't see the material.
How about normal?
Okay, fine, good. So good afternoon, everyone.
Good
I
afternoon.
want to welcome I want to welcome us to another class. I think this should be the second class. I apologize for being absent in the last class. I was in the middle of something that kept me away. Fine, we are going to meet up, okay? I think we've said so many things and we talked about spiro compound and how to name cyclo compounds. And the assignment was given for you to have hands on. So go back. So Eniola, we are working together today. So whenever I say you should go to the next slide, help me move the slides. You're moving the slide. I did not say you should move. Eniola, go to the first slide.
Okay, ma.
So
Yeah.
this is continuation of the class, yes. So today we're going to look at cycloalkanes. We're going to know about their isomerism. Now, in cycloalkane, just like in your aliphatic cyclic alkane, now we have isomerism. Well, we know what isomerisms are, right? Like twins that differ with one thing or the other. So we call them isomers. So isomerism is a phenomenon where you have a compound that have the same molecular formula, but they are different in their arrangements. In this isomerism, we are going to look at cis and trans. So their difference is in spatial arrangement, in their arrangement of one of their atoms in space. So we are going to look at the cis-trans isomerism in cycloalkane. The rotation about cis bond in cycloalkane is limited because of the ring system. Remember, in straight chain, there's no limitation in alkanes, normal alkanes, aliphatic alkanes, because they are straight chain. But because of ring, that ring system is what bring about the limitation. So we can this limitation is going to bring about our isomerism to be around that CC bond. So it cannot pass that CC bond. Now, if we are going to have either cis or trans in a compound, when this is particular substituent, remember we're talking about along the same ring. So anything that is off the ring become a substituent. So if we have more than one substituent and they are arranged on facing the same phase, we call them, they are in cis form. If they're in opposite phase, we call them trans form. Get to the second slide. Now, this is a typical example. We can have this is dimethyl cyclopropane. This dimethyl cyclopropane, because we have cyclo ring, but in that cyclo ring, we have two attachments. When these methyl are the same side, they are on, and when they are opposite themselves, we say they are in trans form. So remember, unlike in the aliphatic alkanes that we know about, it's not all about the ring. It's about the movement or along that continuous carbon chain. When anything that is off the continuous carbon chain becomes a substituent. And when these substituents are facing the same side, we say it's cis. When they are adjacent, we say it's trans. And this one is along the ring. So that's different bit. So next slide. If moving too fast, the slide number 3, we are going to Eniola, please. No, the previous slide.
The previous slide.
Go to the previous slide. Yes. No, the next slide.
Okay.
Okay, is it? Okay. Okay. Now, cycloalkanes. I think the slide I shared is different for what I have, but we can deal with it. Now, cycloalkanes. There are things that we omitted, but it's fine. I think I rearranged them. Okay, let's go. Now, in these just like what we talked about, we've just talked about them. These are alkanes that have carbon. So, are you sure this is a ring? This is a. Are you sure of the what you're sharing? Is it the one of today?
You just sent this to the group, ma.
Yeah.
Yes. Let me check
Okay.
again.
Check again because this is not the slide we're supposed to be using.
Yes,
So
ma'am.
I'm just surprised. Is it the same thing with the one you have?
We've done this last week.
That's what I'm saying. This is not the slide. This is not the slide. Check whether it's the one
Like
I sent.
the slide comprises of what we've done last week and what we are supposed to do today. Probably. Like if
Okay.
you continue.
I move again. The next slide. I move again. No, this is not the slide. Sorry, no. This is not what I supposed to send. Okay, no, this is not what I supposed to send. Hold on, sorry. Sorry, let me share another slide. This is not what I supposed to send. I'm just surprised. No, this is not that. This is not what I have. Okay, I think there was a mistake somewhere. Sorry. Let me sort it. Give me a few minutes. Let me sort
It's
it.
been a mistake, ma'am.
Elon, I think there's a mistake. Wait, I'm sorting it now. I'm sorting it. There's a mistake somewhere. Sorry. There's a mistake. Let me sort it. I'm going to share the PowerPoint. Somebody help me convert it. This is not the class I prepared. Oh, shit. My devices are misbehaving. Apologies. I'm going to sort it. And you want to send to me strong. Eniola, just continue. Let me be. Just continue share. Let me share the new one to you. I have to
Okay,
go through my mails. So yes, continue. I'll be telling you to skip until you get to where we're going. Yeah. I'm sharing the new one now. It's still like that, so that we can. Sorry, we're just moving. This is not what I have. Just continue moving. Continue. Don't those ones. Those ones we can just continue to get where is these serial isomers. Okay. Okay. Okay, go to the next slide. We talked about this. Just talked about. Go to the next one. Now, stereoisomerism. Yeah. I think we can. Then I'm going to share the other slide as I'm sharing already, so you can get the comprehensive one for today's class to avoid confusion. Because there's some things I added to them to make it much more comprehensive. Now, we're talking about stereoisomers. I'm going to be distracted today already. Okay. Now, in stereoisomerism, where compounds can be connected, like we talk about, either in cis and trans. And we also talk about constitutional isomers. Now, I want to differentiate, make you understand the difference between stereoisomers and constitutional isomers. Stereoisomers is the one you're very familiar with. Either we are talking about cis or talking about trans. But when you're talking about constitutional isomers, you're talking about like in normal isomerism, you talk about straight chain and branch chain. That is when you talk about chain isomerism. So this chain isomerism is what we are regarding as constitutional isomers. So difference is the link of the connection of atoms in order. But this one is partial arrangement. Stereoisomer is arrangement in either opposite or the same direction. Then constitutional is connection with link, either on straight chain or branch chain. So let's get to the next slide. Get to the next slide. Now, this is example of stereoisomers. Now, previous slide. I'm not happy with this slide I'm using because that's not the slide I want to use. Let me download the other slide. I'm going to share the PowerPoint with you, and you help me convert it and share it. So we can use it to because there are some assignment classwork we need to do there. And that's why I can't flow with this.
Okay.
Yeah, I'm sharing it now to the group. Exporting to PDF is always getting. I'm sorry for all this. I'm so sorry. But the class will be very interesting because the way I prepared it will be easier for you guys to understand. So conversion is not time. Conversion fast. Okay, now I'm sending it to you now, to the platform, the new. Okay, please help me share it first. Please help me share it first, okay?
Okay, ma, but I haven't received it yet.
Yeah, check the platform now. Have you seen it?
Okay, yes, I'm finished.
Yeah, please help me, thank you.
Downloading.
I think before the next class, I will just share the material before the class. I'm sorry for this. Okay, so thank you, Jerry. So now what
Yes.
we're talking about isomerism in cycloalkane. Well, we are going to have cis and trans to talk about this. And the next slide will give you an example of the cis and trans isomerism we can have in alkanes. Just like what you know about of cis and trans in our normal alkane. Difference is this is a ring. The next slide. It's a compound with atoms. Now, if your question asks, what are stereoisomers? Stereoisomers are compound with atoms connected in the same order, but they differ in three-dimensional orientation. Now, listen. Difference between constitutional isomer and stereoisomer is this three-dimensional rotation. So you make sure you know how to define stereoisomers. And you should be able to differentiate between constitutional isomers and stereoisomers. Difference is that three-dimensional that we have in stereoisomers. Your attendance as you go. The next slide, let's see example of stereoisomers and constitutional isomers. Now you can see the constitutional isomers. The different connections are between atoms. While in stereoisomer, we're talking about dimensional geometry, 3-dimensional geometry. So this one we're just like talking about your chain isomerism, where you have branch chain and straight chain. So that is the constitutional isomers. Why in stereo isomer you're talking about spatial arrangement, 3-dimensional geometry. So just understand and know how to differentiate between the two. The next slide. Now, in the last class, we were talking about, I think I'm going to give you guys a assignment on spiral compounds. And these are another example I want you to lay your hands on. If you should be able to do this, I know that no question will come that you'll not deal with. Now, in this, I want to help you, giving you some clues on how to answer questions like this. Remember, in the last class, we talked about, when you talk about spiral compound, you're talking about a compound that has two rings that are connected. Now, this connection is that point that you normally put in a square brackets. So now, whenever I'm doing this, I should consider the functional group. I should consider the substituents in making my S. Now, if I look at the first one that had hydroxyl group, I don't have any issue because I have to start by giving the hydroxyl group the minimal number. So it's going to be number 2. So I cannot give it number 1 because if I give it number 1, the carbon before the hydroxyl group is not going to have number. Remember, following S, I'm not going to come back to it. So my hydroxyl group becomes number 2. Everything follows sequentially. And when I'm naming this, I will follow the normal method of naming compounds, in the sense that irrespective of the position, I must also go alphabetically. This is alcohol. Because functional group there is alcohol, hydroxyl group gets 2 all. But that doesn't mean that my bromo must come before my chloro in naming, irrespective. But good enough, from the movement, you can see that even bromo comes before chloro when you're moving from hydroxyl to the chloro. So this one will not give you issue. But look at the last compound. The second compound is similar to the first. If you can do the first, you can do the second. The third one does not have issue because just have only one substituent and there is no double bond. But the last compound is a compound that can be dicey. Why will I say dicey? Now, because if I start from that compound that bears methyl, my S will not going to fall in. And if I start from down, I'm going to have methyl to be carbon number 4 and double bond carbon number 5, which is not good. So my S is going to take another shape. My S is not going to face front, it's going to face down. So I'm going to give my double bond carbon number 1, my T is 2. So I'm going to go in that direction to have my S. So if you name it, so I've given you the clue. If you have question on that, I want you to do that, this assignment, and submit. So I've given you a clue on how to solve that last question. Other ones are not difficult. The last one is very dicey. If you follow the mechanism that we've been dealing with the first one and deal with the last one, you're going to miss it. Any question on that? So we're going to get to the next slide. This is your classwork. I just wanted to throw light so that you understand what you're doing when you're doing it. If you have any question in spiral compound, you were not there for the first class, ask the question now, because we're not going to talk about spiral compounds again. Be free to ask your questions. If there's no question,
how did you?
Okay.
Ma, you said we're going to draw the S from down. How, ma?
Yeah, because now the last one. I'm not going to start from the way, normally if you put this compound up and I want to draw my S, what will my methyl be? What position will my methyl be? Answer. If I want to name, on the normal way, if you want to name this compound, what position will you give the methyl? So we can be on the same page. The class can answer. 3. Now that's what I'm saying. If you give it 3, double bond will be number what?
3.
4.
Double
three?
bond will be 4, and it's wrong. Remember, double bond is a functional group here.
Yes, ma'am.
How will it be
And
4?
so now double bond is the functional group. So you're going to give double bond priority. So I'm going to start by giving double bond number 1. So I'm going to go is it clockwise now, not anti-clockwise? So my double bond is going to be number 1, one methyl number 2. So I'm going to go in that round and say form my S. Do you understand that?
Yes, ma'am.
Yeah, so that's what I mean. So whenever you see a compound that is spiral compound, if there is functional group, give it a priority. Make your S following the route that will give that functional group the minimum number, as long as S is maintained. And remember, you don't start S halfway and say just like the first structure, because hydroxyl group is a functional group, I will give it carbon number 1. No, because that carbon before hydroxyl group is missing already in S. So I have to carry it along. Because hydroxyl group is in the middle, I will give it carbon number 2, because that carbon number 1 must go. So I must make sure I maintain the S. Do you understand what I'm saying? Because I cannot come at the end and still go up again. I have to come down. So because of that, I must make sure everything that is up follow. Remember, I talk about S. So everything now, because of the last one, my functional group is in the first one, I'm first compound, I'm following anti-clockwise in naming my S. But in the last one, I'm going clockwise in drawing my S because of the functional group. So what gives me the link or the direction for my S is the position of the functional group. But if there's no functional group, I can go anywhere. Then I will give the substituent the priority, just like whenever you're naming your compounds. Then whenever there is functional group, it gives priority. In the absence of functional group, follow the route that will give the substituent minimum number. So the same thing applies here. Any question on that?
Yes,
Thank you, ma'am.
for the third compound, if we are
Okay.
to give the substituent priority, we are going to also name clockwise. We have to go clockwise too.
Yes, remember, yes, you're going to go clockwise. So you understand it now. So whenever you're naming, that's what you do. But remember, we talk about cyclocombo whenever we're naming, the one that had the highest number of carbon takes priority. So irrespective of talking about the one that has the highest compound having the methyl, if there is no substituent anywhere, I will still start from that bigger compound because it has higher number of carbon. Do you understand what I'm saying? Whenever you have 2 rings, spiral compounds, one can be 6, one can be 5, like we have. Assuming there is no substituent, the one that is 6 must still have priority. You have to make it a parent compound, starting your numbering from that because it has the highest number of compound. Other one follows suit. So we still start from that in naming. So because there is substituent here, we're going to start from that, giving it minimum number. So the carbon number, structure number 3 and 4 is going clockwise. Is that okay?
Yes,
Yes,
ma'am.
ma'am.
Any confusion? Okay, fine. Let's continue. So that's how to name it. This is another assignment. Now, just like we talk about, go to the next slide. Now, this is another assignment. You should be able to know what you're looking at here. You know what is expected of you here. We just talk about stereoisomers. That's what you're really expected to do here. So you're going, whenever you're naming the compound, you must put either cis or trans in the name of the compound you're naming. So that's what you're expected to do here, and it's part of your assignment. I'm trying to give you clues. So when you see something like that in the exam hall, you're not put out. There's nothing there. Name your cyclocompound the way you're supposed to name it, but consider the stereochemistry, whether it is or trans. The first compound is what? What's the stereochemistry of A?
Trans.
B.
Cis.
Cis. So just name the compound. Before you name it, just put cis or trans in front. That's how to name the compound. Remember, it's a cyclocompound. You must put cyclo. Whenever you're naming your cyclocompound, please don't forget cyclo. And whenever you're naming spiral, don't forget to put spiral. Because some of those things, if you omit it, you are going to miss your mark. Nomenclature is the easiest section of questions in this course 319. And the mark. So whenever you're naming, sure you observe the comma when you have die. number to number, comma, number and letter, hyphen. Please make sure you observe all those things, okay? Make sure you, that's why I say, I'm giving you all this stuff, put them on your own. Don't copy from somebody. If you can do all those things you're told to do in class, when you enter exam hall, it will be as if you're in the class. That is the essence of it. Because if you don't have A in this course, I'll be mad with you. At least, what is the least person that the brain cannot accommodate structure should go with B. Because whatever we are talking about in the class and assignment is virtually what will come out in the exam. Just make sure you follow suit. The next slide. This is another assignment. Now, this one, now, whenever you see these two things, how do we know the one that is open, cis or trans? Who can tell me? Who can tell me what's the A and B? What is stereochemistry of A and B? What is stereochemistry of A?
Cis, when you're on the same side. Well,
Cis.
Just what is A?
it's just normal.
Cis.
What is stereochemistry? Cis, A? Is A cis?
It's just normal. There's no cis, there's no
Cyclo.
trans.
Oh, no, there is stereochemistry. Look at it very well. Now, let me explain to you. Now, when you see a cyclochrome, whenever I see a dotted line and a stressed line, it means that among this H and CH, now look at where chlorine is. Chlorine is in a stressed line, while methyl is in dotted line. Remember, hydrogen is not considered. So what you are considering is the methyl and chloro. And look at the line connecting them. Are they the same? At the line connecting them, the bond, they are not the same. Because they are not the same, they are cis, they are trans. It means that one is at the front, one is at the back. That dotted means something that is behind. So they are not facing the same direction. But look at the B. Look at hydrogen. They are the back, both. Look at the substituents. They are the front. So it means that B is on cis isomer, while A is on trans isomer. Do you understand?
Yes, ma'am.
So whenever you see compounds, look at the lines. When the lines are dotted and one is stressed, it means that they are not on the same phase. They will be on cis. But when they are all dotted, they are all back, they are on the same phase. They will be cis. But when we have dotted and stressed, they are trans. They are not on the same phase. So anything that is the same is cis. Anything that is different is trans. So these are trans and cis. So whenever you're naming the compound, make sure you follow the method of naming. They put trans for the first and put cis for the second. Is that clear? Any question on that?
No, ma.
No, ma'am.
Please, if you have questions, just ask, because it will be my job that everybody will cash out with A in this course. So it doesn't take anybody anything that everybody have A's. Please, let's break record for first time in University of Lagos. So the next one.
Okay.
Ask question. The next.
Okay, ma, I want to
These
ask
are loads of questions.
the substituents, but they are not the same. Does this still mean that they are trans?
It must not be the same. Oh, listen. Whenever you're talking about stereochemistry, the substituent must not be the same. Now, in each of the carbon, any substituent that is not hydrogen, that is what we look at. Now, if you look at the first carbon, the first cyclo compound, it is cyclohex. That cyclohex, if you're talking about now, if you want to name, remember I'm going to give chloro the priority because there's no functional group before methyl.
Yes.
Now,
Yes.
if I go to that carbon that bears methyl, I'll realize that there is only hydrogen there. So in this carbon, if I'm talking about stereochemistry, in this carbon, how many substituents do we have? We only have one substituent and one hydrogen. So this methyl becomes the substituent I'm considering in that carbon. Then I come to that carbon that bears chloro. Do we have any other substituent apart from chlorine? Hydrogen cannot be. So in that case, I'm choosing chlorine. So chlorine is what I'm choosing here, and methyl I'm choosing there. So how are the position of this substituent on those carbons? So that's what to talk about. So whenever you are on normal stereochemistry of alkane, of alkanes, when you're on now, you talk about those carbon that is connected by double bond, the nature of the substituent. Now, if on that carbon that is connected by double bond, I have methyl and ethyl, that particular carbon, what gives me the stereochemistry is the ethyl. And if on the other carbon, I have hydrogen and methyl, on that carbon, what I consider in my stereochemistry is methyl. Now, you talk about the higher atomic number takes priority when you're talking about stereochemistry or 213. The substituent with higher atomic number takes priority. So hydrogen and methyl has high atomic number. Chlorine and hydrogen, chlorine has high atomic number. So that's what I consider as my substituent. If you come to the second compound, I have methyl and hydrogen. I have ethyl and hydrogen. So in that carbon of methyl and hydrogen, methyl takes priority. Then the one of ethyl and hydrogen, ethyl takes priority. So that they become my substituent I'm considering in the stereochemistry of the compound. Is that clear?
Yes, ma'am.
Yeah, so that's how so it mustn't be methyl. So even if I see bromo and chloro in a compound, and I will see another place methyl, that I will consider each of the compound carbon I want to look at. What is the higher the substituent with higher atomic number? That one takes priority on that particular compound, on that particular carbon. The next slide. I'm doing so much now. By the time you're okay with all this and you understand it, the nomenclature aspect of this course, you're not going to have issue on it. So this is another question again we are looking at. So with what I've said now, if you look at D, you can realize that on each of the carbon, methyl is the higher atomic number. So I'm going to talk about their on cis isomer, because if you look at the bond connecting them, they are the same. And look at the C. The bond all of them are methyl, but the bond connecting them are not the same. So if B will be cis, C will be trans. Do you understand? Then
Yes, ma'am.
E is not having any stereochemistry. E is not having any stereochemistry. But anyone that has stereochemistry, you can see the way it's written. E is your normal nomenclature. D is your normal nomenclature. Now, but look at D. D is not normal nomenclature. What can we talk about D? What is the stereochemistry of D?
Trans.
Trans. So you understand? So you know a compound, when you're talking about cis and trans, you can see how they are different. You can see A and E is different from B, C, and D. So that's how it goes. So make sure you practice them.
Thank you.
And Bayer is telling us that because the normal angle of straight chain, the sp3 carbon, is 109. So that any ring, whenever we are dealing with ring, any ring that is close to this 109 angle is stable. So the ones that are lower, negatively or positively, either lower or higher, are too strained. Now, if you look at the ring, the table we have, you can see the strain energy. You can see the ring size. You can see when the ring size is 3, you're no more sharing. What happened? Share so that they can understand, we can follow suit. This is a very, very interesting section, and it's something you must expect in exam. So I will take my time to explain it so you can understand it.
Can everyone see this now?
That's a stability of cycloalkane. What is happening to Eniola? Eniola, what is happening to your screen sharing. Not now that we are trying to round up after wasting so much time. At least in the next class, we're going to dive more into this Bayer string theory. Now, let me be explaining before the ring slide comes. Niola, are you having issue sharing again?
I'm sorry, but
Niola is having
my network keep logging.
yeah, network.
Yes.
Oh, okay. Let me just explain it. We'll continue on the next class. So this theory is telling you that the bond. But keep trying that the bond angle. Okay, good. Thank you very much. Okay. Can you do as if you're expanding it a little so that people can see? Please, everybody should. No, it's too much. Okay,
Okay.
fine. Reduce. Okay. Now, everybody should also open this in their phones. Now, this Bayer is telling us that some compounds are not meant to exist because they don't follow this bond angle of 109. You know, sp3 bond angle is 109, 213. So the Bayer is trying to tell us that the ones that are lesser, like, you know, if you're talking about ring 3, they're talking about 160 degrees, the bond angle. So now, the higher the deviation, the more the strain, and the higher the energy. Now, if you look at the table, the energy of ring 3 is higher than that of ring 4, right? Do you understand what I'm saying?
Yes.
Have you seen the table? The highest energy is ring 3. Now, if you look at deviation of 109 minus 60 is higher than 109 minus 90. You know, ring 4 is 90 degrees, right?
Yes.
So now, the higher the deviation, the higher the energy, because the more the strain. And when it is more strained, it can easily break for reaction to occur. Now, example is what happened to you when you are hungry, you are very strained. You can easily react. Even when thing that is not supposed to make you angry comes, you become angry. Somebody say, but this is not what is supposed to make you react this way. But because you're already stressed or strained, you react negatively. So that's what happens. So whenever you're highly stressed, you can easily be angry. So that is what happened to this ring 3 size. Because of the higher deviation from 109 bond angle of sp3. So it's going to be very strained. So every small thing, it doesn't even need so much energy for the reaction, for it to break, for the ring to break and for reaction to occur. So Bayer is telling us that because cis hexa has I think it's about 106 or thereabout. So it's the most stable because it's almost close to the bond. I think 106 or 108 of it's close to ring size of 109. So that's what is I think, yeah. So that's what this Bayer is trying to tell us. Then the higher ones, you can see the way it's fluctuating. Some of them are up and down. But at the end, we're going to also prove Bayer wrong, that some of the things he said are true and some are not true. So Bayer is telling us why some compound does not exist in real life and why some exist because of the angle. We're going to talk about Bayer. Okay, let's go to the next slide. Let's go to the next slide. Let's go to the next slide. Eniola, move.
Okay.
Move. We don't have time.
All right. How about this?
No. The next slide. Yes. Thank you. Now, this is what Bayer hypothesis of angle strain is talking about. Look at cyclopropane. Deviation is higher. And look at cyclobutane is lower. Now look at cyclopentane is 108. So cyclopentane is more stable. Now, the essence of this stability is that the higher the stability, the lower the reactivity. Meaning that in reaction, if cyclopropane will need 60 degrees to react, cyclobutane, who is going to use something like 80 or 100, cyclopentane will use over 150 because they're stable. So the more deviation from angle strain, the higher the reactivity. That is what Bayer is talking about in angle strain. Let's go to heat of combustion. No. Okay, heat of combustion. This is the heat you release when a compound is exposed or is react with oxygen in the air. Now, Bayer is also telling us about this heat of combustion in terms of energy release. Now, remember, the higher the reaction, the more energy is released. Now, when they are reacting, among the cyclopropane to cyclopentane, which of them do you think will release more energy?
Cyclopropane.
Propane will release more energy because it is highly reactive. And remember, like when you're angry, until you say your mind, you will not calm down. So that because of the stress you have to bust everything out, then you calm down. So that whenever this cyclopropane releases the energy, then it becomes stable. And remember, in that case, the ring will be broken. So we're going to see it in the when we'll be talking details on each of the Bayer's theory in terms of reaction. Let's get to the next one. Do you have another class
Yes, ma'am.
now?
Yes, ma'am. 4 o'clock to 5.
Okay. So I think I'm sorry for what happened today. So Eniola, you'll be sharing this
Yes,
slide in the next class, next week, Thursday. So we're going to deal with everything about Bayer's theory next week. And we're also going to do the classwork on Bayer's theory. But this Bayer's theory is just simply telling us about the stability of cycloalkanes in terms of angle strain, in terms of torsional strain, and in terms of steric strain. So we're going to talk about all the strains. And please make sure you lay your hand on the past questions and make sure you turn in your assignments before, today is Thursday, before Tuesday next week, before, I think, 12:59 on Tuesday, the assignment should be submitted.
Okay.
All right, thank you very much. Sorry for every inconveniences today. Bye for now.
Okay.
Please, attendance, Eniola. I want the